Welcome to this video on the basic information and the simulation of an H-patch antenna using the FDTD method. In this project, we aim to study the characteristics of a small antenna. In this case, it will be an H-patch antenna. We will use the OpenEMS software and the FDTD method to construct and simulate this antenna. The objective of this study was to use the parameters provided in our selected project research paper to simulate our antenna and produce similar results to the research paper. The paper was selected from jpure.org, and it is the analysis of an H-shaped patch antenna, and it uses the FDTD method, or the finite difference time domain method, to simulate it. This antenna was a good candidate where small size and broad bandwidth are required. As an introduction to the H-shaped patch antenna, we will show why patch antennas in general are so important nowadays. In this case, satellites are looked at because they're a type of device that use antennas to convey, receive, or relay signals in space. Satellites have become fundamentally important for our communication system on our planet and beyond. However, with conventional antennas that use wires, they are more expensive and take a significant amount of time and resources to develop. Hence, microstrip antennas were introduced. They have many advantages over the conventional antennas and are used in many applications that we use in our daily lives. The issue that arises with the regular rectangular shaped patch antenna is that any frequency below 2 GHz seems to make the patch design grow too large for viable use. Therefore, many methods have been projected to reduce the size of these patches. The H-shaped patch antenna used in this research paper was studied to have a much smaller size than the regular rectangular microstrip. In this section, the applications and fabrication of an H-shaped patch antenna will be explored. First, we will go over some general applications for patch antennas. The applications for microstrip antennas is constantly growing. They are small, lightweight, and cheap and easy to fabricate. They're also easy to integrate with RF modules, such as this one over here, which are used for applications such as small range wireless networks and home automation like remote light switches. These antennas are also thin enough to be mounted conformally to their mounting structures. Patch antennas are used for a variety of different reasons, such as remote controls for robots and RC vehicles. As you can see here, this remote control is attached to a large square antenna, which would be an array of patch antennas. They're also used in wireless home security systems, GPS systems. As you can see, it's a very good reason to use a patch antenna as they're super thin, which would allow for thinner and thinner GPS systems. They're also used in mobile phones, of course. As mobile phones become thinner, they need to have thin antennas. And of course, as stated earlier, satellite communications. Revisiting the drawback from earlier, when microstrip antennas are applied in the frequency range below 2 GHz, the conventional rectangular microstrip patches start to become rather large, which reduces their usefulness. Although this seems like it would ruin the idea of patch antennas in general, there are some ways to rectify this. There are a few different ways to rectify this issue. These main ones are trying to use a material with a higher dielectric constant for the substrate. The problem with this modification is it will cause an increase in the cost of the microstrips, as well as an increase in the loss due to the use of this high dielectric material. Another modification is to insert a shorting pin close to the antenna feed. The drawback from this one is that it needs to be precisely inserted near the feed, which means it will make creating these antennas harder than before, which is also another drawback, as we want to fix this issue without changing the cheap and easy making of this antenna. One last modification that can be done is to change the shape of the patch itself. In this case, we will be looking at, of course, an H shape. Compared with the other techniques of improving the patch antenna, changing the shape of the patch antenna is at the moment the best solution to this problem for a few key reasons. It allows the patch antenna to still be fabricated cheaply and easily while still fixing this issue. So one shape that these patch antennas can be modified to is, of course, the H-shaped patch antenna, and that is what we explored in this project. Now onto the fabrication of an H-shaped patch antenna. The H-shaped patch antenna itself consists of a few parts. Of course, there's the H-shaped patch, and then there's the substrate that it rests on, which is usually its circuit board that it's printed to. Then there's the probe feed, as seen here, and the ground plane, which is this plane right here, that rests under the substrate. When fabricating an H-shaped patch antenna, there are a couple materials that need to be chosen. First, the material for the patch itself needs to be chosen. The material for the patch is usually a metal, and the higher the conductivity, the better, as the ideal antenna would have a metal that is a perfect conductor. But in reality, this is not possible, so just the higher the conductivity, the better. Next, the material for the substrate that the patch rests upon needs to be chosen. The substrate that the patch rests upon is usually the circuit board that the patch is printed onto. So it's not usually chosen, as there are a few circuit board materials that are generally liked. But its dielectric constant will play a role in the overall behavior of the antenna. Next, the dimensions of the patch will need to be chosen. By varying these dimensions, different behaviors of the antenna can be produced. Therefore, it is important for the fabrication of these antennas to know what the relationships are between the dimensions and the behavior of the antenna itself. These relationships will be discussed later on in the video. Once these dimensions are chosen, it is easy to fabricate the patch antenna. These patch antennas are quite easy to just print onto a circuit board. So notice in this case, the substrate will become the material of the circuit board itself, seen here, as this is a patch antenna array using square patches, whereas ours, we will be using H antennas. It's just shown here to give an example. Next, we will be going over the math behind simulating this antenna. The FDTD method is one of the most popular numerical analysis techniques that is used to obtain solutions to modeling computational electrodynamic problems. It has been applied to a wide variety of problems, such as scattering for metal objects and dielectrics, and electromagnetic absorption in the human body when exposed to radiation. Using this method also allows us to easily translate the working of the equations into code used for programming in software such as MATLAB. In our project, we use the FDTD method to analyze the H-shaped patch antenna. The first step is to divide the object into small equal units so that the fields are sufficiently sampled to provide accuracy. In the next step, we choose a time step to avoid numerical instabilities. Since we need to simulate open space regions in our project, we must limit our simulation region by using absorbing boundary conditions. The excitation in the probe feed is caused due to a Gaussian pulse voltage that is given by the following equation, where t is the time period and t naught is the center time. To find the current in the feed probe, we use a series resistor with the voltage generator. The current and voltage are then decomposed into frequencies by transforming them into the Fourier domain. The input impedance of the antenna can be calculated using this equation here, and a sinusoidal excitation at the probe feed, which is given by the equation at the bottom over here, is used to get the electric current distributions on the patch and the ground plane. These are recorded at one instant of time after the steady state has been reached. After the field distribution has been obtained, the radiation pattern can be readily calculated by using the near field to far field transformation as dictated in the research paper. By changing the dimensions of the H-patch antenna, we can obtain different values for the resonant frequency or electric field. Here are some of the observations. The resonant frequency will decrease due to a decrease in the center strip width D, seen here, but the resonant frequency will also increase with a decrease of the length of the center strip S, seen here. According to the research paper, it was concluded that the reduction of the width of the center strip was an effective method in reducing the antenna size. Furthermore, it was observed that when the side strip width or the side strip length were decreased, the resonant frequency would increase. This was seen when the parameters W and B were decreased independently while all other parameters stayed constant. It was realized that correctly designing the H-patch antenna by choosing specific values for the length and width of its center and side strips, we can obtain the required value for the resonant frequency. In this section, we will show how to simulate a patch antenna. Our group's strategy in simulating the H-shaped patch antenna is to repurpose large portions of the general patch antenna simulation that comes from the OpenEMS tutorial and combine 3 patches into an H-shape for the final simulation. The first step in the simulation is to declare our physical constraints. Firstly, we declared our unit variable in order to ensure all constants are in millimeters. Next, we set the dimensions of the actual patch. This includes the dimensions for the patch itself and also the substrate setup. In our final report, we will modify these values to produce an H-shaped patch antenna with the proper substrate that we need. Next, the setup for the feeding of the antenna, how it feeds waves to the rest of the structure, are declared. Again, we will have to change these for our final project simulation to satisfy our H-shaped design. After this, we set up the simulation box, giving it the constraints that we want to contain our whole structure in. First, we must set the center frequency of the antenna, which is the frequency of the excitation. We must also set FC, which is the corner frequency of this antenna. In the next line here, we are required to initialize the finite difference time domain for our excitation. We then must use a Gaussian type of excitation to recreate a pulse through our declared frequency range from the center frequency to the corner. After this, the boundary conditions for the simulation are specified. We now must set up the mesh grid for the FDTD analysis. Max res is lambda over 20, which is the cell size we will use for our mesh. This is because the mesh should be much smaller than the smallest wavelength used. We then proceed to set up the CAD geometry in all 3 dimensions as seen by this section here. Shown here is a general purpose way to create a singular patch antenna. This basic structure can be repeated 2 more times, tweaking the specific start and stop values in order to construct our H-shaped antennas. This is now the end of the video on the introduction of H-shaped patch antennas. We've gone over the uses for these antennas and how they will solve the issue of when frequency below 2 GHz is used. We've also gone over how these antennas are fabricated and the math used in the simulations for them. We also shown how to simulate a simple rectangular patch antenna, but it was noted how this can be modified to create our H-shaped patch antenna. What we want is our results from our simulations to match the JPR paper's results. In our final report, we will show how close we have come towards their results, and hopefully there will be only a small margin of error.